So this is the third lecture in this 4G course, and today we're going to look at OFDMA principles. So what are the important things that you should be able to do when you finish this particular lecture is you should be able to explain the concepts of OFDMA. You should know how an OFDMA transmitter and a receiver work and how OFDMA is used. We're also going to look at modulation techniques used in OFDMA a little bit more detail in this lecture. So we have 5 sections to cover. We start off by modulation, then we look at OFDMA basic concepts, then we look at the OFDMA transmitter and receiver, and then we look at single carrier FDMA in uplink and OFDMA and LTE. Again, as I've said before, modulation. So the first topic we're going to look at is modulation. Now the basic idea of any modulation technique is to prepare a signal for transmission on a wireline medium or a wireless medium. Okay, so you take a baseband signal, because it's not possible to send a baseband signal directly over a wireless medium through an antenna. We have to convert that baseband signal into a form that can be carried over the interface, and this process is referred to as modulation. So you can see here that we have the message signal that goes into the modulator, and it's multiplied by something called a carrier signal. The carrier signal is a high frequency signal, and then that modulated signal is transmitted over the air interface, and then at the end at the receiver we have to do the opposite of the demod, and that's referred to as the demodulator, and we're able to extract. Now this is something that you would have learnt many times over before, so I just wanted to revise it just in case you haven't come across this concept before. Now in the case of LTE, we use quadrature amplitude modulation, or QAM, and there are 3 variations of quadrature amplitude modulation. We can either use something called QPSK, where one symbol is represented by 2 bits, or we can use 16 QAM, we can use 16 QAM, or we use 64 QAM. So these are the 3 possible modulation schemes that can be used in LTE. Okay, and this is both in the downlink as well as in the uplink direction. Now, just as a matter of principle, the diagram below shows the important difference between amplitude modulation, frequency shift keying, and phase shift keying or differential phase shift keying. So essentially, when you have a high frequency carrier, which it's referred to as the unmodulated carrier in this particular case, we can either carry information in the amplitude of that carrier, and that's referred to as amplitude modulation. So for example, when we have a 0, we transmit a signal with a low amplitude. When we have a 1, we transmit a signal with a high amplitude. And this is the basic idea behind amplitude modulation. Now generally communication does not work very well when we use any form of amplitude modulation, because noise affects amplitude most. So the 2 other properties of a carrier that we can change are the frequency of the carrier and the phase of a carrier. So the diagram here shows frequency shift keying. What we do is when we have a 0, we transmit a low carrier frequency, and when we have a 1, we transmit a high carrier frequency. So essentially what we're doing here, we're keeping the amplitude of the carrier constant, but we're changing the frequency of the carrier depending on whether it's 0 or 1. In the case of phase shift keying, which is the last diagram, we keep the amplitude and the frequency constant, but we keep changing the phase. Okay, and you can see here when we have a 0, we transmit the original modulated carrier. When we have a 1, as in this case here, you can see that there's a phase change that has occurred. Okay, there's a 180-degree phase change that has occurred to the carrier, and that is referred to as differential phase shift keying. Okay. Now, as I said, one of the techniques that's used in LTE is referred to as QPSK, and in QPSK we have 4 possible symbols that can be transmitted, and these are shown by these diagrams. So for example, so we have a symbol there which corresponds to phase 0, 0, and we have another symbol, third symbol, and a fourth symbol. Okay, so essentially what this means is you are choosing, you still transmitting a sinusoidal carrier of fixed amplitude and fixed frequency, but the phase of that carrier keeps changing according to the user bits. So for example, what we do is we group the bits into pairs. Okay, and if for example we get 2 zeros, we would transmit that phasor. If you get a 1 and a 0, we would transmit that phasor. If you get a 1 and a 1, and so forth. Okay, so essentially what we're doing here is in QPSK we are always transmitting a carrier wave of a single frequency and a single same amplitude, but we keep varying the phase of that carrier based on the user bits that have to be transmitted. Okay, and this is what they mean at the bottom. There are 1 amplitude but 4 phases corresponding to 4 different phases. Okay, and we have 2 bits with 1 QPSK symbol. Okay, so for QPSK we can say, in the case of QPSK we can say 2 bits per symbol. Now another possibility is to use something called 16 QAM, or 16 possible phases, and you can see all of them drawn in this IQ diagram. IQ diagram refers to, I refers to in-phase component, Q refers to quadrature component. Okay, and we can have one of 16 possible phases transmitted in this particular situation. Okay, and you can see here what we're doing is we are taking 4 bits at a time, and depending on, if you take 4 bits at a time, there are 16 possible patterns that you can end up with. And because we end up with 16 different patterns, we can send one of these, for each one of those patterns we can send one of these phases. So here, in this particular case, we have 3 possible. So in the case of 16 QAM, we have 16 possible phases. 3 of them, the ones in the center here, these ones here are very similar to QPSK, so 4 different phases, all of the same amplitude, and then you have another set of 8 phases outside that, but again those 8, those 8 on the outer, in the middle circle all have the same amplitude, but they have a different amplitude to the ones in the middle. And then you have a third circle of phases. Okay, so here this is a 16 QAM pattern. So sorry, one thing I should say, in 16 QAM we have in 16 QAM we have 4 bits per symbol. The next possible constellation which is used in LTE is referred to as 64 QAM. And in 64 QAM, it's more complex. Okay, here we take 6 bits per symbol. Okay, so we take 6 bits and represent it by one symbol. So here we can see that we not only have differences in phase, but there's also differences in amplitude. Okay. In order to use the 64 QAM, the channel quality has to be very good. Okay. So LTE has this capability by which, if you have an excellent channel quality, it will tell you to use 64 QAM. If your channel quality is not so good, but still reasonably good, you will be asked to use 16 QAM. And if your channel quality is really bad, it will tell you to use QPSK. So this is called adaptive modulation. Okay, so the modulation technique that is used can change from 1 millisecond to the next millisecond. Okay, on a millisecond by millisecond basis, the channel modulation, the modulation scheme can change. Okay, so 3 modulation schemes that are possible in the LTE scenario. Now, one of the things that happens is, you can see if you have 2 phases, as in this diagram here, if you look at these 2 phases, they're very close. Okay, there's very small difference in amplitude, and there is a very small difference in phase. Now, noise can cause, you may transmit phasor corresponding to the 6 ones. This might be the phasor that you are transmitting. Okay, but because of noise on the wireless transmission, the amplitude and the phase of the signal could be changed, and what you might receive is this. Okay, so then you have an error, and you can see how many bits will be in error. 1 bit. Okay, so if you look at the difference between the 2 bit patterns, there's only a single bit difference. So when we design these constellation diagrams, and you can have a look at the previous slide, you can look at, if you look at most of the adjacent constellations. Okay, so for example, if you pick any 2 adjacent constellations, you'll see that there's only a single bit difference, because noise can cause one of the phases to be received as an adjacent phasor. Obviously, if the noise is very high, then first of all you should not be using something like 64 QAM. But if the noise does affect it, there should only be a 1 bit error. Okay, if the noise is very small level. And then there are other mechanisms inside LTE to deal with those kinds of 1 bit problems. So this is the point. If the wrong state, the important point here is this one here, which says if the wrong state is selected, there are errors in reception. Okay, now to account for these kind of errors that can take place, we also add coding. Okay, so data is encoded with parity bits. Before you transmit any data across the interface, we add extra bits which contain enough information so you can, even in the presence of errors, as long as if there are small amounts of errors, you can still recover the original signal. These are referred to as parity bits. There are many different error coding schemes that can be used, and one of the things associated with this encoding is the word coding rate. Okay, so coding rate refers to the number of useful bits divided by total number of bits. So for example, you can have different coding schemes. You can have a coding scheme of half or 2/3 or 3/4. Okay, so what these mean is that in the case of 3/4, it means you take 3 useful bits and you transmit 4 bits. So you've essentially added, for every 3 bits, you've added 1 bit for error control purposes. Okay, we move further. Now, I told you that there are 3 possible modulation schemes that are used. So we have QPSK, we have 16 QAM, and we have 64 QAM. Okay, now the question is, when do you use which scheme? Okay, now that depends on the quality of your radio. Okay, if you have a good radio signal, if the quality of the channel is very good, then you can see that if I were to draw a vertical line here, I could use QPSK, I could use 16 QAM or 64 QAM. But it is, in terms of spectrum efficiency, which is maximizing the use of your spectrum, 64 QAM is the best one. Okay. Now, if the radio link quality were to drop, okay, if the radio link quality was to drop to somewhere here, okay, again, if I were to draw a vertical line, you can see that 16 QAM has the best performance. So when the radio quality is average, you might use 16 QAM. And when the radio link quality is poor, which corresponds to somewhere here, and again, if you were to draw a vertical line, you see that QPSK gives you the best performance in this case. Okay, and this is something that is performed in LTE, and it is referred to as link adaptation. Okay, we adapt to the channel quality or adapt to the link quality. Okay, now in the case of LTE, as I said, we have 3 possible modulation schemes. Okay, QPSK, 16 QAM, and 64 QAM. But we also have a number of error coding schemes. Okay, half, 2/3, 3/4, and so forth. So for each one of those schemes, we've sort of divided the channel quality into 15 possible levels. Okay, and these are the numbers that are referred to here as CQI index. So the CQI index can go from 0 to 15. 15 corresponds to the best possible channel quality, in which case we can use 64 QAM, and we need to put very little data protection. Okay, and the coding range, you can get maximum data rate in that particular scenario. And so this corresponds to the best channel quality, the best modulation, and the least amount of error coding. Okay, because the least amount of error coding means the least amount of overheads that you are putting into the data. Whereas CQI 1 corresponds to the worst possible channel quality, in which transmission is still possible. So here you are using QPSK, and you are also using highest amount of error coding, so that you are adding more bits. In fact, you are putting more error bits than useful data bits. But still, with that, you can get a 78 kilobits per second channel in that particular case. Okay, so this is the so we move on to section 2. After we do section 2, we'll probably take a break. So I'll just ask you to hold on till then. Okay, now if we go further, we see that in the context of OFDMA, we can either use FDD or TDD. Just a little bit of recap for those who are not familiar with this. time division duplex means that you always transmit on the same frequency band, but you separate the uplink and downlink in terms of time. So for one portion of the time, we transmit on the downlink. For another portion of the time, we transmit on the uplink. So we only need one bandwidth or one part of the spectrum for that. This is used in WiMAX. Now, and it's also, there is, in LTE, there is a TDD version and there is an FDD version. Okay, so for example, in China, they have decided to focus more on the TDD version of LTE. Okay, and also in some other countries. Now, in Australia, also Optus is looking at using TD LTE, but Telstra has gone with the FDD mode of operation. So in FDD, what we're doing is we have two separate bands that are separated in frequency. So the uplink and the downlink are separated in frequency, and there's a frequency separation. So this kind of techniques are used in wideband CDMA, CDMA 2000, and so forth. Now, the other question is, what sort of frequency band is LTE going to be deployed in? So the 3GPP specified that LTE should be deployed in existing IMT 2000 bands. These are that every time a new technology comes up, an operator should not need to buy new spectrum. They should be able to use existing spectrum that they have purchased before. They've spent millions purchasing. They should be able to reuse those bands. Okay, so the LTE, apart from the existing bands, there's also bands specified, the 2.6 gigahertz bands. There's a band of frequencies for between 2500 and 2570 for uplink, and between 2620 and 2690 on the downlink. Now, the other important aspect of LTE, apart from the frequencies at which it can operate, is the bandwidth. Okay, so the bandwidths are scalable. So it goes from 1.4 to 3 to 5 to 10 to 20 megahertz. So this means that different operators, for example, an operator who may have a large chunk of spectrum might go straight into 20 megahertz operation, whereas a smaller operator who might not have much spectrum could still deploy an LTE solution with a smaller bandwidth. Obviously, the larger the bandwidth that you have, the more the users or the higher the capacity that you can support. So again, flexibility not only in terms of the frequency of operation, but also flexibility in terms of the bandwidth that can be used. Okay, here's a table on slide 16. You have a table that shows all the possible frequencies that you can use. So you can see bands 1 to 17 is FDD, and 33 to 40 is TDD, mode of operation. Okay, and there's a slide on iPhone as well, which is probably not that important for me. Okay, eNodeB hardware could be operational at 700 megahertz, 900 megahertz, 1800 megahertz, 2.1 gigahertz, and 2.6 gigahertz. Okay, these are some of the common frequencies where they can be used. Now, one thing you'll know from your knowledge is that as you go to higher and higher frequencies, okay, path loss starts to increase. So that means your cells become smaller. Okay, so that's why a lot of operators are trying to, there is a band of frequencies here which were previously used for TV transmission. Okay, and as analog TVs get switched off, a lot of operators are trying to get their hands on these bands, because the lower the frequency, the higher the cell size. So the higher the cell size, the less number of cells, equipment that they need to deploy. So it all comes down to costs. Okay, providing good coverage within a reasonable cost, which are two important metrics in mobile communication. Okay, just before we start going into OFDMA, just to recap, and most of you should know this, some of the first generation mobile communication systems were primarily FDMA based. So in FDMA, every user had a chunk of frequency band, and only that user was allowed to transmit. But the main problem with FDMA systems is that they don't make efficient use of spectrum. So in 2G systems, for example, in GSM, we started using TDMA, where on every frequency we started having the concept of time slots. So each user is allocated a time slot, and until you finish your call, you had access to that time slot. Then in 3G, we started using the idea of CDMA, CDMA2 or wideband CDMA. So here the basic idea was that everybody transmitted at the same time and on the same frequency band, but every users were separated by different codes, and these codes had a property called orthogonality associated with them. That was in 3G. Now we move on to 4G, and in 4G we start using something called OFDMA. And the basic idea in OFDMA is that we have this idea of subcarrier. So it's a sort of an evolution of FDMA, but we have brought the subcarriers even closer together, and I'll explain to you in a few minutes how that was done. So basically, we talked about a symbol before. We said in QPSK, one symbol represents 2 bits. In 16 QAM, a symbol represents 4 bits, and so forth. Now, each symbol is transmitted on a subcarrier. Okay, and so, for example, on a particular if you allocate a particular subcarrier, so in this case, if we allocate subcarrier 1 to user 1, for example, then the user will transmit their first symbol, okay, and that symbol will either have 2 bits or 4 bits or 6 bits based on the modulation scheme that we are using. Okay, so if you're using 16 QAM, for example, this symbol that UE is going to transmit will effectively contain 4 bits of information. So how is it possible? How did remember I told you OFDMA sort of evolved from FDMA. In FDMA, in frequency division multiplexing, okay, so this is the term that I'm in FDM. We had each user being allocated a chunk of frequency, and we also had to put this idea of guard bands, frequency guard bands, between various transmissions, so that one transmission does not interfere with the other. Now, in the case of OFDM, we want to get rid of these guard bands. So we're trying to remove the frequency guard bands, because these guard bands are wasted spectrum. We're not doing anything on it. So what we do is we bring these subcarriers even closer together in such a way that they do not interfere with each other. Okay, and in order to explain that, why do we do that? Well, if we can bring these subcarriers closer together and even get them to overlap, we can put more. Okay, so it's just like if you have a group of people standing, okay, if I put a gap between each one of you, then I can only fit maybe 1,000 people inside this room. Now, if I get one person to stand behind each other, so there is no guard bands in between, then I can pack more people into this room. Okay, so that's the basic idea. The basic idea is trying to pack more information within a specific spectrum that you have. Okay. So in order to understand this, we need to go a little bit back into some things that you've learned many years ago. For some of you, for others it may be new, so you may have to relearn it. So in telecommunications, we have this time domain and frequency domain. Okay, so we can take a sinusoidal, if you take a sinusoidal signal, like the one shown here, if you take this sinusoidal signal here, and if we take that into the frequency domain, that corresponds to a single line in the frequency spectrum. And similarly, and that process is referred to as fast Fourier transformation, FFT. So we'll see this term FFT being used quite a bit in a OFDMA system. So FFT is a process by which we can take a signal in time domain and convert it to frequency domain. And we can do the opposite as well. We can do the inverse fast Fourier transform, and that can take a signal from the frequency domain back to the time domain. Okay. So if you have a pure sinusoid, now this will only happen when with an infinite pure sinusoid. So if you have a pure sinusoidal wave, that in the time domain, if it corresponds to a sine wave, in the frequency domain it corresponds to a something called a direct delta function or a delta function. Yeah, I think those of you who are doing transmission systems, you're probably doing a little bit of this in transmission systems. Now, if you take a square wave signal, and if you were to take the Fourier transform of this, you get something called a sinc function. Okay, and that's the waveform of a sinc. Okay, now how can we use this idea? Now, if we were to increase the width, if you were to make this the width of the square wave, then the sinc function starts to shrink. Okay, a subcarrier. There are two properties associated with the subcarrier. If you were to take a subcarrier, there's the period, as well. There's two things here. There's T and there's T2. Okay, T2 is the duration of the sine wave, and T is the period of the sine wave. Okay, so the period of the sine wave corresponds to the center frequency. Okay, whereas the duration of the sine wave corresponds to the width. So we can change as we increase the duration. If you were to increase the duration of the sine wave, then the width of the sinc function will decrease. Now, how can we use this idea? This is basically what happens in OFDMA. If we pack these subcarriers in such a way, now you can see that if I were to take one subcarrier here, okay, so this is basic. Each one of these could be a sinc function basically. So I'm taking one of these sinc function and placing it here, and I'm adjusting so that the second sinc function is sitting somewhere here. But what you'll notice is at the point where this sinc function has a maximum value, all other sinc functions have a zero value. They all pass through that point, so they don't interfere. Okay, so this is what I meant by the fact that we can pack our subcarriers even closer together by using this idea, because we make sure that the tails of a sinc function has a 0 value at all points at which the adjacent subcarriers have maximum value. Okay, so mathematically you can explain it this way. So if you do this, one subcarrier is not going to affect the adjacent subcarrier. Okay, we can get rid of this interchannel interference. Okay, now in FDM systems we keep the band separated by a guard band because we don't want transmission on one band to affect the transmission on the other end. But what we have done here in this case is we have designed our subcarriers in such a way that there will be no such interference. So we are bringing our subcarriers even closer in such a way that there is no interference. Okay, and this is a key point here. The interchannel interference are cancelled. Subcarriers can shift. Okay, remember, how does frequency shift occur in communication? There is something called Doppler shift. Okay, so if in the case of a UE moving in a car, okay, there could be some UEs that are transmitting on a subcarrier where they're stationary, and there are other UEs who are moving in a car and they're transmitting these subcarriers, and they've shifted in frequency. Okay, and that can cause a certain amount of interference. Okay, and there are mechanisms to get over that. Okay, so the basic idea is remember this domain here. What is this domain in? This domain is in the frequency domain. Okay, we haven't started talking about what's going to happen in terms of the time domain. Okay, so what's happening here is that maybe one user is transmitting on this subcarrier, a second user is transmitting on the second subcarrier, a third user is transmitting on the third subcarrier. Just to give you a basic idea of what OFDMA is all about. Now, not all the subcarriers are used for data transmission. Majority of the subcarriers are used for data transmissions, but you also need subcarriers for pilots. Okay, sometimes it's necessary for the receiver to synchronize in frequency, and you need pilot subcarriers for that. You also need something called a DC subcarrier, and a DC subcarrier is something that is used to initially synchronize to know the centermost frequency in the band. Okay, because we have so many different bands in which it can operate. So the DC subcarrier is used for that purpose. So it's used by the mobile device to locate the center of the OFDM frequency band. And you also have other subcarriers. Some of the subcarriers you may have are guard subcarriers. Okay, another problem that we have in OFDMA is intersymbol interference. Okay, now interchannel interference means interference between one channel and the other channel. Intersymbol interference refers to transmission from one UE. Okay, because you've got to transmit one symbol, then you've got to transmit the next symbol, and so forth. So what is the possibility that one symbol from one UE does not affect the next symbol from the same UE? Okay, and the main reason why we have this is because of multipath. Okay, so often you have a direct path between the UE and the E node B, but you also have a reflected path. Okay, and when we have a direct path and a reflected path, we have a phenomenon called multipath occurring. Okay, so this symbol here, you can see, for example, if we were to take the example of this particular symbol here, okay, you have the version that arrives directly, and you have the red one. The red one is the one that has come through a reflection. Okay, and the reflected one is going to arrive slightly behind in time, and it may also be of a smaller amplitude, because in the process of reflection you lose some of the electromagnetic energy associated with the wave. So you can see that at the receiver you are going to get two waves arriving, and they have different amplitude, different phase, and so forth. And this can cause an error. It can cause something called intersymbol interference, or ISI. So again, this occurs only within one subcarrier, okay, from one symbol to the next symbol within the same subcarrier. So how do we overcome this problem? Well, we overcome this problem by putting a guard time between each symbol. So we transmit a symbol and we have a small amount of guard time, and these guard times are shown in red here. Okay, so even if the guard time corresponds to the maximum possible spread that you can have. Okay, remember, electromagnetic waves are all traveling at the speed of light. Okay, but so you can estimate within a small cell or within a large cell what is the maximum spread that you can have. And people have done research on this, and they have calculated the appropriate guard time that is needed for small cell and large cells. Okay, and we put this in so that these times here, this particular time which you see in gray here, this is referred to as a guard time. So even if a symbol was to arrive slightly behind in time, a reflected signal was to arrive slightly delayed in time, it will not have an impact on the next symbol that's going to be transmitted. Okay, now somebody did some research on this and found out and did quite a bit of simulations and test runs, and found out another way that we can implement the same thing. Instead of transmitting nothing in the guard intervals, what they did was take the last portion of the symbol. Okay, so they would take this portion of the symbol and copy it into the front of the symbol. So you can see what's happening is that this portion of the symbol here, which is the last portion of the symbol, has been copied and transmitted over here. And this results in better performance than if you were to transmit nothing. Okay, so this guard interval is also referred to as a cyclic prefix, and the cyclic prefix enables easier demodulation. And what we do is we make a copy of the last part of a symbol and stick it in the front where the guard interval was going to be. Okay, and this technique has been found to be quite useful in OFDMA to avoid the problem of intersymbol interference. So now we move to section 3 of lecture 3, and we're going to try and put some of the ideas we've discussed so far and put them together. So we initially said that we start off with some bit stream that's made of ones and zeros, and then we do some encoding, and we primarily do encoding for data protection. So for example, in this example, they have taken 4 bits of user data and add 4 parity bits, because we are using a code rate of half. The next thing that we might do in this particular case is we might be using QPSK. So we take every 2 bits and represent it by one QPSK symbol. And these symbols then go into something called a serial to parallel unit. So we convert a serial signal made up of multiple phases. We convert each of those serial signals into a parallel signal, and we also channel map. So remember, we may have a 20 megahertz spectrum. So we move different. Once we do that, the next thing that we do is, because we've got a parallel frequency domain signal, we do a inverse fast Fourier transform on it, and we convert the signal from a frequency domain back to time domain. So for example, what could happen here is that the first bit that corresponds to 1, could be transmitted on subcarrier 1, for example. The second bits could be transmitted on subcarrier 2, and so forth. And these bits go into the frequency to time domain transformation, and we go again back from serial to parallel. Okay, so we are combining all of these subcarriers together to get this output. And then the last thing we do is we add this carrier prefix, cyclic prefix, which is added to overcome the effect of multipath, and then the signal is transmitted. So these are the basic building blocks. Okay, the actual system is far more complex than this, but you can think of these as the basic building blocks of an OFDMA transmitter. Okay, you start off with a bit stream, and you go through this various process of encoding, modulation, serial to parallel converting, and mapping to different parts of the spectrum, and an IFFT process back to a serial signal to which we add a carrier prefix, and then we transmit it. At some stage it will have to be moved from IF back to RF before it's transmitted. Okay. Now the reverse has to take place at the receiver. So at the receiver we receive a signal. So the first thing is we've got to synchronize both in terms of time and frequency, and then we remove the cyclic prefix that we added at the transmitter, and we then do an FFT on that signal, and then we do the subcarrier demapping, which is what was done in the transmitter, and then we demodulate the signal, and then do exactly the opposite. So if we modulate at the transmitter, we do demodulation at the receiver. If you do interleaving at the transmitter, we have to do de-interleaving, and if you do encoding at the transmitter, we've got to do decoding at the receiver. Okay, and we come back to our bit stream. Okay, so it's quite a lot of complex operations that have to be performed, and as I told you in the first lecture, one of the reasons why OFDMA was not implemented before was the technology to implement this level of signal processing was not cheaply available to be put into a handset, and until recently, only recently has that been possible, and hence OFDMA has become a technology that can be used in mobile communication. OFDMA as a technology existed many years ago, 40, 50 years ago. It's been around. Okay, but the most important thing is can you develop a handset within a reasonable cost so the man on the street can afford it, and that was only possible more recently. Technology that's used in the uplink. So in the case of, we said that OFDMA is used in the downlink, but in the uplink in LTE we use a different technology called single carrier FDMA. Now the main reason we use this is we can find that out by looking at some of the advantages and disadvantages of OFDMA. So OFDMA is very good because we are transmitting a very narrow band. Okay, so it's robust against narrowband co-channel interference, and we saw how we align the subcarriers in such a way as to minimize interference between channels. We've also seen how we have overcome the effect of intersymbol interference by the use of cyclic prefix, and the fact that we are overlapping spectra of various signals means we have high spectral efficiency. Okay, and we've now been able to efficiently implement the FFT processes so that it's available to the man on the street. But the main problem that we have with OFDMA is it has this problem called high peak to average ratio. Okay, and this is referred to as PAPR. Okay, so it has a high PAPR, peak to average power ratio. Now what does this mean? Well, let's just take the case when we have different users that are transmitting, okay, at the same time. Remember, all users are transmitting at the same time, but maybe on different frequencies. Okay, and in this case, if you were to add all these signals together, we will get an output that looks like that. So we see that at some points we are transmitting a signal with a high power, and at other times we are transmitting a signal with low power, and this is why it has a high peak to average power ratio. And so they decided that this is not good for uplink transmission. The main difference between downlink and uplink transmission is, in the downlink transmission we are transmitting from an E node B, and usually there's power supply there, so battery is not a problem on the downlink transmission. Whereas on the uplink transmission, it's being transmitted from a mobile that has, where we have to make sure that the battery lasts for as long as possible. Okay, and so for that reason, people did studies. A lot of people did probably their PhD in this area, and they tried to find a better modulation scheme than OFDMA for uplink, and they came up with this idea of single carrier FDMA for that. So single carrier FDMA has a reduced power amplifier cost for the mobile, and by reducing the power amplifier back off, you also get an improved coverage for that. Now, in OFDMA, we have this notion of subcarriers that are overlapped, okay, and each user might be transmitting a symbol on one subcarrier. Now, the idea was then, what we've done in single carrier FDMA is that we've taken each user's transmission and we've spread it across all of the subcarriers, or many of the subcarriers. Okay, so each user, essentially, instead of using one subcarrier, they're using multiple subcarriers, but only for a fraction of time, a much smaller fraction of time compared to OFDMA. Okay, so this diagram is probably not that very clear, so I've put in another diagram here which sort of explains that. So you can see that the idea that we talked about earlier, where we have symbols being transmitted. So we have a symbol here, we have a symbol here, we have a symbol here, and a symbol here. Now what we've done is, so you have a user that is transmitting. One user may be transmitting on this subcarrier, another user might be transmitting on this subcarrier. This summary at the bottom probably explains it a little bit better. It says OFDMA data symbols occupy 15 kilohertz for one OFDMA symbol period, whereas in single carrier FDMA, data symbols occupy M into 15 kilohertz. M can, in this particular example, M is equal to 4 for 1/mth of the symbol period that was used in OFDMA. Okay, I'm going to skip this slide. So in terms of processing, how will the processing differ in the case of OFDMA and single carrier FDMA? So we saw that in the case of OFDMA, we take the symbols that are coming in, and we have a serial to parallel converter, and the serial to parallel converter essentially converts the serial information into parallel form. So it sort of sends a 0 and a 0 there. The first two symbols go there, the next two symbols go on this line, the next two symbols go on this line, and so forth. Okay, this is the serial to parallel conversion, and then this is transmitted as an OFDMA symbol. In the case of single carrier FDMA, we don't do this serial to parallel conversion. We just apply the FFT on. We can have 5 megahertz, we can have 10 megahertz, and so forth. And the number of subcarriers, remember, subcarriers is what we allocate to users, actually groups of subcarriers. So far we've been saying that each user gets allocated one subcarrier, but strictly speaking, each user gets allocated a group of subcarriers. So what each user gets is the same idea is used in. So we have this idea of resource blocks that are allocated for users, okay, both in the downlink as well as in the uplink. Okay, and the number of subcarriers. Okay, now whether we can have different spectrum allocation. Okay, we can have 1.4 megahertz, we can have 3 megahertz, we can have 5 megahertz, and so forth. And if the subcarrier spacing is 15 kilohertz, okay, we can have number of useful subcarriers will change. Obviously, if we go with 20 megahertz, we will get 1,200 subcarriers. Okay, so generally, the larger the bandwidth, the more the number of subcarriers, and these other aspects refer to the sampling frequency, okay, as well as the number of symbols subcarriers per FFT.